Evaluate the triple integral over e of y squared z squared dv, where e lies above the cone, phi equals pi over 3, and below the sphere, rho equals 1. Above the cone, phi equals pi over 3 tells me that phi is going to be between 0 and pi over 3. No mention of theta tells me that theta is going to go from 0 to 2 pi. Now this cone has its vertex at the origin, which means that rho is going to have a value of 0 at its lower limit. And then since we're talking about the solid below the sphere, rho equals 1, we know that the upper limit for rho is equal to 1. So rho is going to be between 0 and 1. Now we weren't asked to draw the region, but I'm going to show you what it looks like because I want you to have an idea of how a triple integral in spherical coordinates is actually working to sweep out a volume. Now we're told that the cone has an equation phi equals pi over 3. By the way, that means, look at that. That's the simplest equation you're ever going to see for a cone, right? That's a side effect or a benefit of working with spherical coordinates. Folks, this is a wide cone. How do we know it's a wide cone? Because phi is an angle made with the positive z-axis, and if phi is pi over 3, that means we have an angle of 60 degrees from the positive z-axis, which means that the edges of this cone are 30 degrees off of the xy plane, right? Now, we said that theta goes from 0 to 2 pi, so that's going to give us all the way around, right? It's a circle all the way around. And I could ask the technology to make this a better looking oval. I won't. I'll just try to draw a better looking oval. I'm going to let this be a little bit rustic because I want you to see, like, how would you do this on your own without this technology? And then we're underneath this sphere, rho equals 1. So now I need to give this a dome. Essentially, this is an ice cream cone. It's a really wide ice cream cone, but we have this spherical dome above a wide cone. Now, how this sweeps out volume. Now, of course, this integral that we're doing here is not volume because we have an integrand y squared z squared, right? But we have this dv. So how is dv working to give us volume? Say, let's imagine that instead of y squared, z squared, that our integrand is 1. Okay, rho goes from 0 to 1, which means rho starts at the origin and has a maximum value that is on this sphere. Now I'm going to reproduce this picture so I can add to it. And then I also had to shrink it up because I'm going to give you a third picture in just a minute. But first, let's talk about how phi is working. Phi goes from 0 on the positive z-axis to pi over 3. And so we'll say that this sweeps down the sphere and gives us this edge of the cone, right? There, I'll leave it like that. So with rho going from 0 to 1 in this case, and then phi taking that 0 to 1 and sweeping it down from 0 to pi over 3, that essentially gives us this, I don't know, it's not like a paddle in there. It's a pizza slice shaped planar lamina. That's what that is. Now, I'm not sure I can convey what I'm trying to convey right here, but now let's consider how theta is working. Theta sweeps around, and as it does, just in the same way that phi sweeping down gives us this planar lamina, theta sweeping around gives us the solid. Now that we have that down, let's evaluate the integral. Let's not forget our integrand is y squared z squared. So our integral is going to have phi going from 0 to pi over 3. I'm going to see if I can squeeze it in here. So there's my d phi. Theta is going from 0 to 2 pi, and there's my d theta. Whoops, put it in the wrong place. D phi should be the outermost integral, differential for the outermost integral. My bad there. And then rho goes from 0 to 1, and that's our innermost differential. Our dv, remember, includes rho squared sine phi. So all of that is our dv. And now we need a y squared and a z squared. Remember, y is rho sine theta sine phi, so y squared is rho squared sine squared theta sine squared phi. Z is rho cosine phi, so z squared is rho squared cosine squared of phi. Yay, we fit it all in. Let me just adjust this a little bit. And now that's our integral. No way I'm computing it this way. Our entire integrand is a product. It's just a series of factors, right? So we can gather together all of the rows. We can separate out the sine squared of theta. And we can gather together all of the phis. We can express this as a product of three integrals. And in fact, I'd like for you to do that and then evaluate it and then come back. And by underlining, I left out a sign of phi. I hope that didn't throw you off. I have the product of three integrals from 0 to the pi over 3 sine cubed of phi cosine squared of phi d phi times the integral from 0 to 2 pi of sine squared of theta d theta times the integral from 0 to 1 of rho to the 6th d rho. That, folks, turns out to be 1/7. The rest of it, folks, we have an odd power for a sine function, so I'm going to break off one sine and I'm going to convert the sine squared of phi into 1 minus the cosine squared of phi. That makes my u the cosine of phi. My du is negative sine of phi, and so when I distribute the cosine squared, I rearrange the order of the terms. We now have the integral from 0 to pi over 3 of the quantity cosine to the 4th of the phi minus cosine squared of phi times the negative sine of phi d phi. Next integral times 0 to pi, 1/2 of the quantity 1 minus the cosine of 2 theta d theta, applying the power reducing formula on the sine squared of theta. These integrate. I pulled the 1/7 out front. Cosine to the 4th of phi times this negative sine of phi d phi is going to give me 1/5 cosine to the 5th of phi. Likewise, cosine squared of phi, we get minus 1/3 cosine cubed of phi. That's going to be evaluated from 0 to pi over 3. And then integrating with respect to theta is probably the easiest thing after the 1/7. So it's the second easiest thing of 3, right? Whatever. Anyway, 1/2 of theta minus 1/4 sine of 2 theta from 0 to 2 pi. Putting in either 2 pi or 0 in place of theta for the sine of theta is going to zero out that term. As for the rest of it, grab a calculator. Remember, the cosine of pi over 3 is 1/2, so you got a bunch of 1/2s running around. Final answer here, folks, I get 47 pi over 3,360.